So see, basically, when we talk about thermodynamics, what it means, it is actually the branch of physics that deal with the concept of heat and light. Correct? So I'm really sorry for the handwriting.
Oh, no, it's fine.
Yeah. So what do you mean by heat and light, or you can say heat and temperature? To be more specific, if you talk about, it is like heat and temperature. Correct?
Yeah.
Okay. Now, when we talk about heat and temperature, how do you deal with in thermodynamics is like, suppose if you've studied mechanics, or if you've learnt about it, suppose a car is moving, right? So if a car is moving, what is happening? What energy, or what do you understand? How is the motion of the car, asked or predicted?
Well, the car is moving forward, like it's propelling forward.
Yes, so when it is moving forward, we
Yeah.
take into account first the velocity, correct? Second, the acceleration. So this is all mechanics, what I was talking
Yeah.
about. Right?
Okay, yeah. I think I've learned a bit of this, yeah.
Yes. And the motion of the car. Motion as in, like, although it is, basically connected in this also, like, direction and velocity, speed and direction, but yes, velocity, acceleration, and motion. Correct?
Yeah.
But in thermodynamics, if I say that if a car is moving, what am I going to do? I am going to take into account pressure, okay, temperature, all right, and maybe the third thing is volume.
Yeah.
Okay, so this is the basic difference between the thermodynamics and mechanics. All right, so that is what it is. Okay, now when we talk about, when you are talking in the terms of thermodynamics, or these things, this is actually called macroscopic science. Okay, now why do we call it macroscopic science? Because we deal with bulk systems, huge systems, right? Like volume and temperature, both are macroscopic quantities, or you can say the values.
Yeah.
Okay, why am I saying this, Swapnil? Because in the later part of the chapter, you will be actually covering about heat engines and all, and these are like bulk quantities, and that is why we say macroscopic.
Why are they called bulk quantities?
Yes.
Why are they called bulk quantities?
Yes. So bulk quantities because they are huge, more.
Okay, yeah.
Yes. Like heat engine is big, right? So that's what I said, because first you'll have to understand the laws. Then we'll go to heat engine, and then you'll explore each part of it and learn about it. So there are many things which will come up. Okay. Now, now you have to tell me, suppose when a gun, there's a bullet which is fired from a gun, what happens? If I talk in terms of, say, velocity, or maybe kinematics.
There's the bullet has its own velocity.
So suppose if I say a bullet is fired, okay, and if I have to talk in the terms of kinematics, what is going to be calculated? Any idea?
You calculate the velocity of the bullet.
Very good.
And it follows a straight forward motion.
Yes, the motion. Super. Okay, but if I have to talk in the terms of mechanics, so this is mechanics, sorry, thermodynamic form, in the thermal form, then
Mhm. Maybe like the air pressure in the gun or something,
okay.
or
So
maybe
yes,
the
all
temperature of the gun after firing the bullet. Not sure.
yes. So hit it on the right part. Why? Because when you said that the bullet is fired from the gun, it is
Uh-huh.
pierced in the wall. What is happening? The kinetic energy of the gun, I mean of the bullet, is converted to heat energy.
Yeah.
Okay? And not heat, we
Uh-huh.
actually call it thermal energy.
Yeah.
Right?
Yeah.
Yes? Okay. Now, what happens is there is a condition of equilibrium. Okay. Now, have you heard about what is equilibrium? Any idea? What will be equilibrium?
I've heard it in multiple subjects, like when I'm doing economics and things like that. But maybe it's when like wait. So what are we talking about with equilibrium? Like the thermal energy?
Okay. I'll relate it to kinetics or mechanics, whatever you want to say. Both are
Uh-huh.
same only, kinetics or mechanics. We
Yeah.
say when the net force is zero.
Okay. Yeah.
Okay. When we say
Yeah.
the net force is zero, then the system is in equilibrium.
Equilibrium. Yeah.
Correct? So
Yeah.
same way in the macroscopic values, that means the variables. What are the macroscopic variables? Volume, pressure, temperature. Correct? So what are the three macroscopic variables? Pressure, volume and temperature. These three, if they don't change with time, right, then the system is said to be in equilibrium. Correct?
Yeah.
Yes, or you can say they don't change, or you can say when these three remain constant. Okay, so what I'll do is I'll write P, that is pressure, volume and temperature is constant, which doesn't change. Then we say the system is in equilibrium. Okay, so till here is it clear?
Yeah, it's clear.
Okay. All right. Now, again, this is again divided into types of equilibrium. That is thermal, chemical, and the third part will be mechanical. Okay. So, thermal equilibrium, chemical equilibrium, and mechanical equilibrium. Okay, I'll change the pen, I think. Black, that will be more suitable. Okay. So thermal equilibrium means when temperature is constant. Okay. Then when we say chemical equilibrium, that means the composition of the system does not change with time. So I will come to it, what it means, like composition of system. So technical it sounds, right? So composition of the system does not change with time. Okay. And the last one, mechanical pressure is
Mechanical
uniform.
is net force, right?
Yes, uniformity of pressure. Correct? So now, when we have to talk in the physics term, we say if the system is in thermal equilibrium, chemical equilibrium, and mechanical equilibrium, then the system is said to be thermodynamic equilibrium. So
Mhm.
these three has to be in the equilibrium. That means all three has to be constant. Then it becomes a thermodynamic equilibrium system. Correct? Now,
Mhm.
what is happening, Swapnil? I am actually constantly using a term. I said composition of a system does not change with time. So what do you think is a system? ये किसकी बात हो रही है? What do you think? I mean, why are we talking about system? What do you think it will be?
Uh, a system. I'm not sure. I'll just get like kind of guess. Is it like the thing that
Yes.
you're talking about? Like if you're talking about like a engine,
Okay.
then that'd be a system. I'm not sure.
Okay. Anything else you can think of? So system is right. I mean, the answer which you gave, engine, that is right. But more specific, you've just given one example of it. Anything if you want to generalize or something?
Isn't it just like an object that you're kind of studying the use of physics on or something like that?
So basically, Swapnil, when I talk about a system, it is any portion which is enclosed by some boundaries and which can exchange things, where exchange can take place. So what I said, I'll repeat it once again. The definition, I'll repeat it once again for you. It is any portion of a body, you can say, which is enclosed by some boundaries. So this is the boundary I'm talking about. This boundary, and through which the exchange can take place.
Okay.
Now, what do you mean by exchange? Exchange of what? Exchange of heat. Exchange of what? Heat. Okay. So when you have to talk about like anything other than the open surrounding is a system, right?
Yeah.
So for example, if you talk about a glass, you have put tea, water, hot water or something, warm water. What happens after some time? Your tea becomes cold,
Cold.
or your warm water becomes at the room temperature, or it's not that hot again. Why? Because there's a transfer of heat. So see, this is also a system. Why? Because this is a body, you can say, which is enclosed inside a boundary. So what is the boundary? Like a glass shape. Okay. And it can exchange heat. How are they exchanging heat? The water or the tea or milk or coffee, whatever is there inside the, glass, and the surrounding area. So surrounding area is the room temperature, and whatever the temperature is there inside the glass, it is getting, the exchange of heat is happening. Easy?
Yeah.
Okay. So now you can tell me, like, what is a system? Can you just repeat it once again for me?
Any portion of a body which is enclosed and you can exchange heat. Was it something like that?
Okay. Now, when we are talking about these kinds of system, they are actually, again we say, there are types of system. Okay. So there are three types. One is open system, one is closed, and one is isolated. Okay. So can you now imagine and tell me something which will be a open system. Some example, like I gave you an example of a glass or a tea, and a closed system and an isolated system. Anything, any example, can you think of it?
Okay, so one for open system, a closed system, and isolated system.
Yes.
So a closed system would be like something which doesn't have like an opening. So maybe like a closed box
Okay.
with that's filled with like hot water or something.
Okay.
And then isolated system, maybe it's
Okay. So basically, I think Swapnim, a little more pressure if you put, I think you'll be able to get it, but that's okay since you are studying it for the first time. I will tell you. So open is open, the surroundings, right? Which is an open system. So basically open in the sense where there is a transfer of heat and energy. Both are transferred. That's an open system. All right. The example of a glass, which I gave you just now. Okay. Closed system. Yes. You have any question?
No.
Okay. Closed system where only heat will be transferred. Sorry, not heat actually. Only energy will be transferred, not heat. Okay. Only energy. No heat will be transferred. Okay. And isolated, no heat and no energy. Complete isolation. दोनों नहीं होगा. Both of them. Okay. So as I told you, example of an open system was a glass. Now can you think of example of a closed one where only energy is transferred, no heat is transferred?
Like I'm not sure. Is it not a? Is my one from before not a closed system?
But what is it?
Like
where only energy is transferred, no heat is transferred. Okay. So we'll do one thing, Swapnil. I'll put this one for you as a homework, a very small homework. Okay. Example of a closed system. Think of it and tell me in the next class. Okay. If you don't get it, I will tell you. I'll give you 5 examples of it.
Okay.
Okay? All right.
Yeah.
Now the third one. Can you think of the third one? Isolated, no heat, no energy.
No heat, no energy. It's just empty bottle or something.
Empty bubble. No.
Oh, maybe is it like a vacuum? Maybe.
Okay. Vacuum. Almost correct. Vacuum where? Live example. Real life example. Can you quote something? Okay. Maybe. 5 seconds. Very good. Almost there. So yes, you almost hit it, but couldn't get the right this thing. That's a thermal flask. Right?
Oh, okay. Yeah.
Yes. What happens? You keep hot water or a tea and you even open it after 2-3 hours or maybe 5 hours, it still remains hot only, or a hot
Yeah.
case, right?
Uh-huh.
So these are the examples of isolated. No heat is getting transferred and no energy is getting transferred. You get the material as it is. It's as hot as it is. So yes, it is like a vacuum. It's like thermal flask. It is isolated. The surroundings,
Uh-huh.
you keep it anywhere, move it anywhere. Like suppose generally thermal flask are, we take it for patients who need tea and coffee, and you put it or pour it in the bottle and take it to the place, it still remains the same, correct? Because there is no surrounding energy or surrounding heat which is getting transferred and coming back to it, correct? So this is the example. All right, open, closed and isolated, correct? Okay.
Yeah.
Now when we are talking about a system is in thermal equilibrium or not, it depends upon two things. Okay, so first is the surroundings, the universe, the surroundings where the object is placed. Okay, suppose you place a cup in Kerala or Chennai side, and you place a cup in Shimla or this side, or maybe in your place, Australia, or maybe Canada. So the time will be like in Chennai, it will take time because the weather temperature, the weather conditions are, the temperature is high, 42, 45. And that side it is 0, minus. So it will take a second to cool down, right? So yes, the first thing it depends upon is surroundings. The second thing is the nature of the wall separating it. Nature of the wall separating what? Separating the system and the surrounding. So I will write it for you. Separating the system and surroundings. Why am I saying like this, system and surrounding? By the nature of the wall we are talking about, Swapnir, because when you're talking about the thermal flask, right? So the wall which is created is so good or so adaptive that it doesn't let the heat and energy to be transferred outside, right? But when you talk about a cup, the energy or the heat is getting transferred. And how this happens? The temperature of the heat, I mean the temperature which is more, it gets transferred from a higher temperature to a lower temperature. Always remember this. How does a heat is transferred? From high to low. Always. Okay, so I'll repeat it once again for you. See, if the temperature of the water is high and the temperature of the surrounding is low, okay, so transfer of heat will take place from the higher temperature to the lower temperature. And that is the reason, Swapnir, that the water which is hot becomes in the room temperature. Okay, it will never happen that low temperature will become high. No. Okay, so this point you have to remember. It comes like in question, heat is transferred from high to low or low to high. Okay, done? Shall we move ahead? Okay, so quickly tell me this about the nature of the wall which plays an important part. Very, very important. Okay, so nature of the wall. Now you will say, okay, nature of the wall, what does that mean? Yes, so one is known as adiabatic. wall. Okay.
Adiabatic.
Yes. And the second one is called diathermic wall. Okay. So when I'm talking about these terms, have you heard these terms or no?
No.
No. Okay. So adiabatic means insulating. Okay, the spellings and the handwriting is going really bad. Okay. So insulating. That's what it means. The pen is not working properly. That's okay. Fine. So insulating wall which does not allow heat to flow from it, right?
Yeah.
Which is known as thermal flask.
Yeah. Also, can you describe other stuff apart from the walls as adiabatic? Like if you were writing about something else and you wanted to say that it was insulating, then could you say it was adiabatic?
Yes, I will describe everything. Don't worry. I will come to it. Okay. Diathermic, which has a conducting flow. Okay. Which has a conducting flow. Conducting flow means it can pass easily from this to this, from this to this. Correct? So when we talk about these things, as you said, you want to learn more about it. So that's what we will do. So let us begin with adiabatic first of all. Okay. So when I'm talking about an adiabatic wall, it is a system, say A and B. And this is your wall, which is shaded this way. Okay. And here it is P1, V1. Now I will tell you what is P1, V1. That is pressure 1, volume 1, and this is temperature 1. Okay. Secondly, it is P2, V2, and the temperature is T2. Okay. So when I say no heat from A to B, there is no transfer happening. Correct? When I'm talking about this, that means the transfer will not take place. And that is why what I did is I just shaded this area. This is like brick. You can't go from here to here. Not done. Okay. Here what will happen? The temperature will not change. Will not change. Why? The temperature will remain the same. Your coffee or tea remains the same. Correct? The hotness. So that's why it will not. Yes. So basically in this place temperature will be constant. If not changing, that means constant.
Wait, so in which place? In the shaded area?
One. Yes, temperature. This place.
Okay.
Shaded area is your wall.
Okay.
This is your wall. Which wall? Adiabatic wall. The insulating wall. And this is your system 1. This is your thermal task, and this is your, maybe surrounding or whatever.
Yeah.
Okay?
Yeah.
All right. So pressure and volume will be same, and temperature will be constant. Okay. Now, when I talk about same thing for a diathermic. Okay. So diathermic, same thing. There's a system A, there's a system B. Here also P1, V1, P2, V2. And this time what will happen is, it didn't changed. This, the transfer is happening, right? After some time the heat flow will take place from where to where? From A to
A to
B.
B.
Correct? From
Yeah.
where to where we are talking about? From A to
A,
B.
B.
This is a
Yeah.
conducting flow. This, when you talk about, this is a conducting flow, you can say. And this wall which you talk about is a diathermic wall, which allows the heat to pass on. The example of a hot water in the glass. Hot water in glass. Okay? So,
Yeah.
I mean, there will be a flow of heat till the time they both reach at the same temperature. So in that one, temperature was not changing, but here temperature will change and it will try to be exactly the same like T2. Both temperature has to be same. It comes at the room temperature.
Yeah.
Correct?
So
Yes.
they both have to be same for it to stop transferring. Is that what you're saying? Okay.
Yes. So basically, actually, this is just the introduction of all these things. You will actually learn about the laws of thermodynamics. Like
Yeah,
first
I don't think
law.
we've gone through
Yes.
that yet at school.
Yes. So when you talk about those laws, no, you should be aware of these things, because there we will talk. In the zeroth law, what happens? In the first law of thermodynamics, what happens? What are state variables? So these are a lot of things which we have to explore. Okay, so this is like, today is more of like an introduction. You are understanding what is a system, what is a wall, which wall doesn't allow, which wall allow. Because when you'll be doing numericals, you will get questions like this. There's a diathermic wall which the heat is this for this system, and the temperature for the second system is this. What will happen? So these kinds of questions will come. So that's what you are actually learning the terms today. What is adiabatic? What is diathermic? And all. Okay. So now, Swapnil, since I have less time, I mean, we have 10-15 minutes more. So instead of starting the laws of thermodynamics, what I will do is I will teach you the equation of the state. Okay. So why equation of the state? Although it should come with the thermodynamics first law and all, but before that I want to explain you zeroth law, and I want to start, and I feel the time is less for it. So I'll take you to the equation of the state first. Okay. So just so that you can start doing few numericals if you want to attend from the same section. Okay. So why am I doing like this? I'll go directly here. Okay. So here, no, the equation of the state is always written this way. PV is equal to RT. So why this? Because we say pressure and volume are directly proportional to T, and this is being replaced by a constant which is called R. So it becomes PV is equal to RT, and this is also written as PV is equal to mu RT, where mu is number of moles.
I see.
Yes. So I will come to it, why number of moles and everything. If you've heard, if you've read about this in your chemistry. So this is all related to pressure, volume, temperature, and the constant.
I think we went to that, but instead of M we used N, I think. PV equals nRT.
And this is actually called the equation of state. Okay. And this equation which I'm talking about, PV is equal to mu RT, this is actually the equation of an ideal gas. Okay. Now you will say ki why am I discussing about these state variables and all these things. All these things are being talked about in the thermodynamic state variables like
Mm-hmm.
pressure, temperature, volume. These
Yeah.
are all what? Internal energies.
Mm-hmm.
Okay, and these energies, you can divide it into two types. Okay, that is
Mm-hmm.
extensive and intensive. So I'll take you over there. First you just write this equation. This is called the equation of the state. You can just note this down, and then I will take you to the other things. Okay, noted.
Mm-hmm.
I'll move forward, change the slide.
Yeah.
Okay, so now when we are talking about these equation of a state, so what do you mean by a state here? So here it is actually called thermodynamic state variable. Okay, so now when I'm talking about thermodynamic state variables, it is what? It is determining the equilibrium state of a system. State variable means you will tell the state of a system. I'll repeat it once again. Thermodynamic state variables
Yeah.
are determining the thermodynamic equilibrium state of a system. Example, pressure, temperature, volume, mass, and internal energy. Okay, and a system is not in equilibrium, cannot be described by a state variable. So if the system is not in equilibrium, then you cannot describe it or tell its state variable. So basically, when you have to determine all these terms, pressure, temperature, volume, mass, internal energy, there is a mandate that the system has to be in equilibrium. Then only things will work. Okay. Now when I move ahead, there are two types of it. Okay. So one is extensive and the other one is intensive. So what do you mean by?
So are those a types of, what are those types of?
Extensive and intensive. So I'll take you over there. What is extensive and what is intensive? So extensive is size of the system.
Okay. So those are the variables.
Yes, size of the system. Not exactly the variables, because when you are talking about, when you start on with the different things, you will understand what is internal energy, what are the different dynamics laws. Then you will understand like heat, energy and power are different things. So there are many things to explore first. Maybe for a cylinder, maybe for a heat engine, maybe for a gas. So there are many things on this. Okay. So that's why we are saying size of the system, not the variable. I think some confusion, Swapna?
Can you say it again, that part?
Okay. See, we were talking about what? Swapna, that we are talking about the state variables. So state variables are what? These.
Yeah.
These. The system is not a state variable. Okay.
Yeah.
These are state variables. The pressure, temperature, volume, mass, and internal energy. Okay. See, before this chapter, you used to think heat, energy, all are same. But here in this chapter you will explore heat is different, energy is different, internal energy is different. All three things you will come to know how they work and all those things, right?
Yeah.
And when I'm talking about these state variables, what will happen is there are types of these. Types of what? The systems. Okay. One is extensive system and you can say one is intensive system. So extensive is size of the system. So basically mass or the number of particles, right? The examples are volume, mass, and internal energy. These are what? These are extensive. And intensive, which does not depend on the size. Does not depend on size. For example, temperature and pressure. Okay. So now when you are talking about temperature, pressure, these will be intensive, these will be extensive. Okay. And all the state variables are not independent. Okay. Why not independent? Because temperature and pressure will be connected some way. We have written this thing, no? PV is equal to mu RT. So see, pressure is directly related to temperature. If you increase the pressure, the temperature will increase, like that. So this is what they are trying to say. Ki all the state variables are not independent.
Yeah.
Right? So this is what is about thermodynamics. This is the basics, the starting. These are the terms which we will be using in and out or throughout these classes or throughout the chapter. Okay.